Okay, hello everybody. Thanks for joining nTop Live. Happy Friday. We're going to be talking about a exhaust manifold that's going to have some combination thermal and structural analysis performed on it. And I think this example should be pretty simple and easy to kind of follow along with. So I'm actually, you should have the file sent out. Or it can be made available afterwards, but we're just going to build this from scratch. So let me bring up a new instance of nTop. Just a quick note, we're on 2.12.15 or 0.5, so 2.12. This past couple weeks or months, we've had a lot of new updates of really great features, including back to CAD and some expanded thermal analysis simulation tools. So I highly recommend you to update using the button up here or app.ntopology.com if you haven't already. So let's name our notebook. Let's just call this an exhaust manifold with thermal and structural simulation. And let's import a CAD part. So if we import this parasolid, it'll look like this, and it is a manifold with some extra faces for kind of connectivity, but all we care about here is some of the faces on this main body and the whole body itself. So I'm going to double click on, with this block selected, I'm going to double click on the body and right click and select create CAD body variable. And then I'm just going to name this our CAD body of the manifold. So if I just isolate this view, we see that. And then there are some faces along here that are going to be used as boundary conditions for our simulation. And so I'm going to select those. So the first one we have is the set of kind of inner faces. That's the first set. So let's select this face. I'm going to hold Control click to select multiple, and then this one. So these three CAD faces are going to be added to a CAD face list variable. So we just right click and select that, and here we have that. And we'll name this the inner CAD faces. I think it might be something else in the file, but that works fine too. It's just a name. So let's do the same for these outer faces. So here, let's do this, control click, and you have these outer faces. So I'm going to right click these and select create CAD faceless variable. So now if we isolate this, we can go back and forth, and you'll see those two faces selected. And so these are going to be important when we're selecting boundary conditions for our simulation. We'll use these for structural and thermal boundary condition locations. Hey, sorry. I just realized I forgot to hit the broadcast button. So we may have missed some people. So I'm just going to quickly start over, and hopefully if you are joining us now, we can start from scratch. And if you don't mind, if you already saw this, then we'll keep going. But let's just import this part. So I'm going to select import part from the search, and I'm going to find this manifold. And this manifold is like an exhaust manifold that could be from an automotive or aerospace application. And this parasolid file has a few things, a main body, and then some faces that are used to align that body probably from CAD. But we just care about this main body. So I'm going to double click here and select create CAD body variable and name it CAD body. And then there are some faces on this CAD part that we're going to use as boundary conditions for our simulations. So we're doing a thermal and combined thermal and structural simulation on this exhaust manifold. So first, let's select these kind of interfaces for the the rings that are going around this manifold. And so I'm going to hold Control and click, and I'm able to select multiple of these features, of these CAD faces, and then just right-click that and select Create CAD Face List Variable. And I'm going to call this Inner CAD Faces. And then we have these outside ones, so we're going to do the same process for that. So select, Control-click, Create CAD Face Variable, and we'll name this Outer CAD Faces. And so like I said, these are going to be used as boundary conditions later. So having these variables of lists is useful. And we don't need to do any more CAD prep. We have all these things laid out. So the body and then the sets of faces. And now we're going to want to mesh this part because it's going to be discretized if we're going to be able to run simulation on it. So what I'm going to do is start with a mesh from CAD body block. And I'm going to drag this down to the bottom, and I'm going to put the CAD body we created in here. The default options are going to be fine here. It'll just take a second to run. So it is converting this CAD body into a like STL style mesh, right? Now, this mesh isn't very good for simulation, obviously. You're going to want to have nice uniform elements. And this is geared towards being efficient and defining the space, but not uniform elements for describing the physics of what would happen with this part. So let's redistribute this mesh or recreate it by using a remesh surface block. So I just searched in the search bar, remesh surface. You see it takes in another mesh because the data types match here. You see this is the symbol for mesh, and it's asking as an input for a mesh because it's remeshing it. So let's just drag this in here. And then we're going to want to specify a edge length for our mesh elements. And you can see this can be a field, meaning you can have this be spatially varying. But let's just use a constant value of 6 millimeters based on the size of the overall part. That creates a reasonable mesh size. And we're going to choose triangle mesh shape. And so if we let that run, while we're waiting on that, we can go ahead and recognize that the mesh size here is going to be a important number that we may want to play with as a user doing simulation and analysis. So I'm going to right click where it says edge length here, and it's going to make a variable. And so now I can quickly go through my notebook, even if this is collapsed and not viewable. I say, oh, okay, the mesh needs to be finer, coarser, so that I just change this. So that mesh is still being created, but while we are going, what's also going to happen is we're not only going to need a surface mesh of the outside surface of the body, but also a volume mesh to analyze what's happening in the internal parts of the exhaust manifold. So I created a volume mesh block by searching in the search bar, volume mesh. And I'm going to use the same edge length that I used for the remesh surface as the volume mesh. So you can see I dragged that variable that we created down into the edge length input for the volume mesh. And I'm going to drag this whole remeshed surface here into the input of the volume mesh. And everything else can stay the same in terms of our parameters. And what we have now is what should look exactly the same as a surface mesh because we are not changing the outside. But if we do a section cut, you can see there are now elements being defined inside the volume of the manifold. So this is a volume mesh. And the last step in terms of meshing is going to be to designate this volume mesh and prepare it for finite element analysis. So we have another block called FE volume mesh. And what that does is it takes in a volume mesh, but then it gives it a either linear or quadratic order for calculations. So you've heard of, linear, whatever order of your finite element analysis is going to happen. Basically, how are you interpolating between the elements when you're finding out the temperature, stress, or displacement of the elements. And so we're going to use linear, and we're going to drag the volume mesh block in here. And just really quickly, it creates our finite element volume mesh, which is ready for simulation. Now, the last step here is I'm going to make this a variable, just like I've done with other things, so it's easily organized and accessible. I'm just going to name this FE mesh. So a lot of these are left default because they're working for us. And if you would like to know more about what these inputs to these meshing blocks do, you can go into the properties tab and look at descriptions here or here. But you can also look at support.ntopology.com, and we have lots of articles on kind of visual representations of what these kind of things do. So the next step we want to do is define a material property. And this is going to be a little different from other examples you've seen maybe, because we're going to not only include structural, but also thermal and mechanical properties. So first, I'm just going to create a isotropic material block. And this block is just, it allows us to fill a list of different material properties and then define a material based on that, right? So material is just a list of a bunch of different properties. And so these are kind of put in subcategories that are things like elastic thermal, and then also the coefficient of thermal expansion, which is kind of a combination between an elastic and a thermal property. But let's start with an isotropic elastic property. So this is going to be your run-of-the-mill Young's modulus and Poisson ratio. And so I'm just going to put some standard values here for a metal. So that's in pascals. So I do 2.1 times 10 to the 11th pascals and 0.3. And then let's add another property to this list for the thermal properties. So let's call that isotropic thermal property. And this is asking for the thermal conductivity and the specific heat. And the units here are a little unconventional. We're coming out with an update soon that will just allow things like watts and better examples of that. But what I'm going to put in here is 45 here, and for this unit. Oh, I'm actually going to copy and paste something that is the unit conversion has already been done. So, unit conversion is not something we really need to go through right now. And for this nTop Live, you can do that on pen and paper, or using Google searching things. But here I have a bunch of units that I've just already laid out mathematically, and it will auto convert into whatever unit nTop takes. So this is kilograms meters squared over seconds cubed divided by meters times Kelvin. And yeah, again, unit conversion can be done by just like typing things in. Like if I put in 6 inches here, it'll auto convert it. But we're also working on either in the next update or the one after having things like watts and joules and things like that in there. So that'll be coming soon. For this input, I'm going to do 0.472, and for the density, we can leave that as optional. As you see, it says in dark gray optional here because we don't need it for any of these calculations. We do need one more property though, so that's the coefficient of thermal expansion, and that's not in either of these blocks because, I'm sorry, that's not in either of these because it's kind of in between both, right? Isotropic coefficient of, there we go. And yeah, so that's like alpha, the units are in 1 over Kelvin, and we can put in a sensible value for our material. And now our material is sufficiently defined. I can right-click this and make it a variable and call this just our material property. And now we need to define a solid model. So if you're familiar with nTop, you've probably done this before. But we're going to create a block here that takes in, it kind of glues together all of the different parameters that we built into something that could be an FE model. And so it needs a mesh, right? So I'm going to take my mesh block and drag it in here, and I'm going to take my material property and put it in here. And that's it, that's done. So the frame has to do with how, if you have spatially varying materials, how it interprets where those are laid out. But since we have an isotropic material with constant properties everywhere, we don't have to worry about the material frame. And so now we need to start selecting boundary conditions for the different simulations that we're going to do, because we're using this FE solid model actually as, you know, something that's going to be used in both the thermal analysis and the structural analysis. And so you can kind of double dip here when you're building your model. But first, first we're going to do the thermal analysis. So let's start selecting boundary conditions for that. And so for this manifold, like I said, it's an exhaust manifold, so you're going to have some hot exhaust gas flowing through here, and you want to understand what's the temperature of the metal throughout here, and then also when that heating up occurs, what internal stresses are going to be put on this design due to thermal expansion. And so before I move on, I'm just going to right-click this FE model block and make it a variable. And let's create a heat flux boundary condition. So that would be, let's see, surface heat flux. And we have a bunch of new, we actually have a bunch of new thermal analysis boundary conditions. All our boundary conditions are listed under simulation under this tab. And you can always just read about them using the info panel under information. But this one's pretty straightforward. It's just, you know, you choose some face boundaries, and then you say that this much heat flux is flowing through that. So that's the unit for this. And again, you know, these units are going to be including watts and joules and things like that soon. So bear with us for that. But you can always do the conversion, you know, pretty easily from whatever method you prefer. But anyway, we need to specify where we are going to have this heat flux occurring, right? There's certain nodes that will have it, or certain faces that will have it, and certain faces that won't. And a useful boundary selection tool is flood fill. So if I double click here, I can see how I can maybe do that, fill in the boundary here, and I'm going to choose flood fill. And flood fill works by specifying a point in space, and then expanding outward and looking for faces that are exposed to that point. So if I have like a point right here, it would search for all the nodes or faces that are you know, moving towards that or facing that point. And so I'll show that in just a second. You should be able to visualize that very quickly. First thing this asks for, though, is a mesh. So let's put the mesh in here. And again, let's select faces. And this origin point is that point I was talking about. So what I can do is put my mouse either in the XYZ position here and drag this around. And since we're looking for a heat flux here, what we want to find is an inner surface. So you see it's already working. If I put it on the outside, it's selecting the outer nodes there. But what I want to do is put it inside here so that we can start selecting these interfaces. And I'm going to cheat a little bit and just look at a number that I know already works, which is 0, 10, 0 millimeters. And you can figure that out from where your CAD file is designed, or you can just move this around until you get it. But as you can see, now we have the inside node selected here. And it travels all the way through from the inlet here, or the one side here, and then the other outlets here. So the last thing we need to do is specify what the actual heat flux is. So we're going to use a positive 40,000. That means it's going to be coming, out from the fluid into the material. So it's the material is being heated by the exhaust gas. And we can see if we zoom in really close, we see vectors here showing, or arrows here showing that's what's going on. We have some hot gas that's transferring heat out into the metal of the manifold. And so this looks pretty good. I'm just going to make this a variable and call it the heat flux boundary condition. And that's not the only boundary condition we need, of course. So we have also convection that we're going to specify. And we're also, let's do the convection. That's it. So we're going to have some heat flux that's coming in, and then we're going to specify convection coefficients on the outside on different parts of the material. And their coefficients are going to dictate how much heat is flowing out. So it's not just all going into the metal and staying there. It has to flow out as well. So we can assume that there's some air traveling around here and get a convection coefficient. But first, before we try to mathematically define that convection coefficient, let's specify where the nodes exactly are going to experience that convection. And so we're going to do a block called convection boundary load. It's basically just saying, there's a coefficient of convection and a ambient temperature. So where is that occurring? And again, we're going to use a boundary by flood fill. So let's specify that same mesh again. I'm just going to check. Yep, okay. We're going to specify that same mesh, and we're going to select faces again. And now we can drag a point elsewhere and try to find somewhere where we're selecting all the right outer nodes. And so here that did that pretty quickly. I am going to specify a point I already checked, which is 50-50, but it's really just, you can see where it is in space. It's just somewhere outside of everything. And so it's able to look around and select all the right nodes, our faces. And by the way, you can go back to the heat flux boundary and see where this point is. So you see it's just peeking inside here, and it's able to figure out, okay, now I'm inside this structure. So I'm going to flood fill the whole thing with selected nodes or faces. So here's the convection coefficient block we're working on. We successfully defined the boundary, and now we just need to specify an ambient temperature. And so we're going to use 300 Kelvin. And this is a useful thing that might change. Your simulation might want to have that as an input. So I'm just going to right click the ambient temperature and select make variable. And now I have this, I can move it up to the top, maybe even the inputs eventually, but that's just there for the user to quickly access. And the same goes for a convection coefficient, right? If you want to change out the material, maybe. Also note, before I do that actually, note that these are both fields. So you can, and that's based on the icon here. So this doesn't have to be some constant thing. You could specify a temperature that spatially varies around here. If you know that it's cooler air or warmer air ambient wise, and the same for if you had material properties that were spatially dependent. So there's lots of information online about how to do that. We're just going to use constant values for now, because this is more focused on just setting up the simulations, but it's worth pointing out. So give me 1 second. Yeah, okay. Let's, again, like I said, put in a convection coefficient. And then I'm going to make this a variable too. So those are sitting next to each other there. And this boundary condition is now functioning where we want it to. And maybe that's not the only place where convection is occurring. Because as you can see, all we selected were regions along the circular pipe area. But the part itself has more than that, right? It has these large faces, and you can imagine that heat might be transferred into them and that convection might occur there too. So let's go to the, let's make this a variable and call this convection BC1, but let's create another one. And there's a couple ways to do that. We could either just type in convection, or we could duplicate variable. So I right click and select duplicate variable. And now this is literally the same exact thing, but let's replace the boundary we're selecting this with something else. Because what we're going to use instead is the CAD faces. So these guys right here, those are going to be specified by as having convection coefficients there, or convection is occurring there. So let's double click here and choose our options for boundary. These are ones we already created because we have the icons here, so that means they're already created variables. The FE face boundary is an option to allow CAD features to be brought in and selected for regions where we want to, have a boundary condition. And so I have these faces. They are going to also be experiencing convection. Now, as you see, this is a list. And you know it's a list because of the icon here of the three lines here, and then the fact that this is the name of the block, but also it has parentheses three items in it, right? This is also a list here. It's waiting to accept a list of however long. But if we drag this inside this, that's not quite right, because that would be a list inside of a list. So what we actually want to do is just get rid of this pre-populated list. So now it's just expecting a new kind of list. You see the icons match, right? There's three rectangles here for CAD face, and that matches here. So I got rid of that pre-populated list because I already have one that works just fine. I don't need to add to a list. I'm just going to replace the list. And I put that there. I'm going to specify my FE mesh. And again, we'll select faces for convection. And now we have these CAD faces as selected convection regions with the same coefficient, and the same ambient temperature that's referencing. So now we have all of our boundary conditions for our thermal analysis. We have some heat flux that's traveling through the inside of the pipe, and then convection with the specified coefficient flowing outside. And the last step is just to create our thermal analysis. So we have a thermal analysis block, and all it is it takes in a model and some boundary conditions, and then it produces a temperature result. So this is extremely easy now. We drag the model in, and then we drag our first boundary condition, our second boundary condition, and our third boundary condition. And voila, we have a thermal analysis performed pretty quickly. I think we have multi-threading for this. And so there you can see, I'm just going to make this a variable and call it thermal analysis. And the result here is the temperature ranging, this is all in Kelvin, but you can see the results nicely laid out here. So you can see as it travels through, the convection gets out more and more, and it cools down a bit. But there's also more convection on this side because we didn't specify this as, or we did specify it all as convective. But yeah, there's the thermal results. I won't try to, postulate too much on my thermodynamics, but that's the simulation results based on the loading conditions we set up. And now what do we do with that? Well, first of all, we may just want to be able to look at what the temperature is everywhere. And so we're going to create a point map. We're going to create a block called temperature point map. And what this does is it takes in a thermal analysis block. You see this input, and it creates a point map. If you look in, these are actually just points that are colorized based on whatever the temperature is. So this is a new feature that we can view point maps like this. I think it's extremely useful. It's not that different from this, except these results, the temperature is kind of averaged between, you can see there's like gradient happening. That's averaged between the data. This is actually just, at every discretized point that defines this manifold, we have the actual value, and we can display cutoff values as well, as you can see here. And so I'm just going to call this the temperature point map. Oops. Temp point map. I'm going to save this, by the way. You should have this whole file complete, but if you're following along, don't forget to save. And now we have this, which is useful and everything, but it is discretized. Both of these results are discretized. And a lot of stuff in nTop can be controlled by fields. So the question is, well, if I have discretized data, maybe from imported simulation or simulation I did from nTop, how do I convert that to a field? How do I make that a 3D and continuous 3D space instead of these little points that are defined at specific locations? So we have a field from point map block, which is basically just an interpolation tool. And I have a video on what these interpolation methods mean. Basically, they're the same as what you see in MATLAB in their interpolation methods, or a lot of open source libraries. But basically, barycentric is really good because it is good at dealing with tetrahedral elements, where you have a value defined at like 3 corners of a triangle or of a tetrahedral. And so it'll interpolate between the values of the tetrahedral really nicely. So that's why we're going to use barycentric interpolation. And we're going to bring in this point map we just created. And now we have a field. We can call this temperature field. And I'm going to just view that to make sure it looks okay. So I'm going to hit F for the field viewer, turn everything else off in terms of visibility. And if we just move this around, you see we didn't use any interpolation. Or I'm sorry, we didn't do any extrapolation. So it's only going to be defined where we have this 3D region where the pipe exists. And maybe I'll try to find a plane that is easily viewable. Yeah, like that's something a little better. But now we can see that basically the same results, just now it's been interpolated into a continuous field as this result. And the reason why it's empty, or sorry, 0 most places is because the pipe is empty on the inside. So there's nothing defined there. But anyway, now we have this field, and this field can be derived as a new feature in nTop for doing thermoelastic properties. So let's just make this a variable, call that temp field. We have that. And then let's set up a structural analysis simulation. And we can use a lot of the same blocks we already created here. But I'm going to create a static analysis block. I'm going to drag that to the bottom of my notebook. And the FE model, like I talked about earlier, it's just ready to go for any kind of analysis you want to do. All it contains is the material properties, which we defined as having a bunch of different things that could be useful, right? Isotropic, elastic, thermal, coefficient of thermal expansion. So that's all packaged up in here, and then it contains the mesh, which we created, And so we can drag this in, kind of double dip for thermal and structural analysis using this FE model block. And now we just need to add some load cases. And so any structural analysis needs some kind of, fixed boundary condition or some kind of, boundary condition to make sure it's not going to fly off in space. And so let's start with a fixed faces. And we have this nice block that allows you to quickly choose CAD faces and fix them in space. And it's called FE fixed faces. So what this block does is it lets you choose some CAD faces like these and say, okay, that's wherever the nodes intersect with these faces, that's where the displacement will be fixed, and you won't have any movement there. So ran into this earlier when we were doing the face boundary here. It's asking for a CAD face list, right? And it's auto-populating it with an empty list just for convenience. But we already created a list. So if I drag this in here, it's not going to accept it, right? We'd be putting a list inside of a list. So we just need to delete this pre-populated block and drag the already created CAD face variable or CAD list variable down in here. And now we're referencing these CAD faces. And we just need to choose a mesh. And in a few seconds, we have, let's see, let's view this. We have these shown as being fixed there. And the static analysis is done, but it's not doing anything, right? It's just saying, don't move this, but then there's no forces or anything. So we need to add another boundary condition to this list. So I'm going to go to this little plus sign to add boundary conditions. And I think you know, if you've been using nTop, you've seen all kinds of different forces, moments, you know, all the boundary conditions for conventional, you know, structural analysis, pressure, bearing force. But something that's relatively new to nTop is adding this temperature, and which is going to cause thermal expansion, which then causes internal stresses. So this kind of thing is really important, not only for making sure that your part isn't exhibiting these internal stresses, which could cause damage, but also in aerospace applications, maybe you have something that a sensor is at the end of this long pole, and you want to make sure when it goes through temperature fluctuations, how much does that sensor move, right? So being able to have temperature drive the displacement in static analysis is really useful. And so this new block I'm talking about is the applied temperature load. So this is a structural block, but it allows you to interface with thermal data. And it's asking for a field. And so I'm just going to drag this temperature field that we already created, right, into here. And I'm going to do one more step. So it will assume, I think this is in the instructions here, it assumes that there is a initial temperature of monothermal. Yeah, it makes an assumption about what the kind of ambient temperature is based on, I think, the average temperature of this field, but we can also just specify what the ambient temperature is for this when it's doing the analysis of how much everything is expanding. And so let's add one more block called initial temperature. And this we can just put as the ambient temperature. And now we have a full thermal analysis driving a static analysis. And let's just call this thermoelastic analysis. And here we have wherever there is temperature, it's going to cause displacement and stress, right? So we can see where that's occurring. And another new feature I want to show off that's also relevant to this is the fact that now our vector maps, I'll just make this first, I'll explain what I did. Our vector maps are viewable in nTop. So if I have a static analysis, what I can do is create a displacement point map, which means it's a vector point map. So there's the nodes at each node location that specifies what's the vector of displacement. So you can go in here and look at actual results here, like happens to be a point at this XYZ location. And then if I go to the corresponding vector for that point, I can see what the actual displacement has been. And that kind of data is kind of, at least in nTop, hard to visualize or conceptualize. But now we have these beautiful arrows. You can change the size of them, but now you can see based on their color and their direction, kind of like a wind map on a, on a weather report. You can see what's going on in terms of the displacement. And you can also put bounds on it or change the bounds. So really beautiful new feature, I think, allows you to see that. So we can call this the displacement vector. And I think that's everything I wanted to cover. One quick extra thing that I ended up doing when I was working on this, I didn't put it in the final file, but I was going back and forth converting the temperature to Celsius and Fahrenheit because Kelvin is not like intuitive to me. And instead of going back and leaving nTop to do that, I decided to just make a really quick tool where I'd take the formula for conversion between Kelvin and Fahrenheit, which is the temperature in Kelvin minus 273 times 9/5 plus 32. And then I use evaluate expression. So now I can put whatever value in. Let's say it's 300K. I'll just make this a variable and call it K to F. And now I can really easily just like, without having to Google it or think about it, just type in whatever that is. So you can build these little tools, put them in a group at the end of your notebook, just reference them or actually build the math into your notebooks. But something that I don't really, I like that I can kind of do whatever I want in nTop, whatever math expression, however simple or complicated. I don't need another program. I could just do it all here. So I think that's everything here. I don't see any questions immediately, but I will pause for a moment and let any questions come in through the chat or through the Q&A. Okay, well, I think that's it. I appreciate your time, either watching this live or in the future. And if you ever have questions about this topic, I'm happy to discuss. My email is blakejohnson@ntopology.com. So that's BLAKEJOHNSON. And if you have trouble getting the files or anything, we'll make sure you get those by just contacting me. And I hope you found this helpful and can take this knowledge and example file and build something cool for yourself. So thank you and have a good weekend.